Up to now, we discussed function define a finite closed interval. So the interval is finite interval, right? But we will encounter problems, especially in partial differential equation problem, that the defining interval will be unbounded. Okay, so we have to generalize the Fourier analysis into that domain. Okay, and then the Fourier series becomes Fourier integral, as we will see. Okay, so now I point out the purpose. So in this section, so we will develop a suitable format to represent a function f of x defined on the right half branch from 0 to infinity of R by extending the method of Fourier series. Okay, so this is the our purpose. Okay. Right. So now, we will let f of x be a piecewise continuous function defined on any so f of x is a piecewise continuous function from any finite subinterval of the whole real line, and is okay, I have to say, we want to represent a function defined on this semi-infinite interval or the whole real line. Okay, to say for all the whole real line. And then we let a function defined on the whole real line, and such that it is piecewise continuous function on any finite subinterval. Because we define piecewise continuous on a finite interval, right? And we say that this function is defined on the whole real line, but if you look at an arbitrary finite interval, the f function, the function should be piecewise continuous. Okay, and also and it has left hand and right hand derivative at every point in real line. Okay? So basically, this is the function that we encountered in the representation theorem of Fourier series. Okay. So f of x is a function defined on the whole real line. And if you look at a finite subinterval, then this function is piecewise continuous. Okay? But the function can be bigger and bigger and bigger, right? Bigger and bigger. And in any such a finite interval, the function should be piecewise continuous. And at every point, the function has left hand derivative as well as right hand derivative at every point in the real line. Okay, so now, so we truncate the function. Right, so the function is that. Okay. So B, the truncation of f of x on the finite closed interval, mass L to L. Okay? So f of L is a function defined only on the finite closed interval. And it's coming from the original function f of x by truncation. Okay? Right? So for every x in between minus L and L, but not including the endpoints, we take the function value to be f of x. At the post endpoint, we just deliberately let the function value to be 0 for our purpose. Okay, just for our purpose. Okay, so now we have so now we can regard f of x as a period of a periodic function. Is that okay? And because at the L and minus L, they have the same value 0, so it will be periodic, repeat again, right? That's the reason why I deliberately define the function value of this function on the two endpoints. Because I want to let this one to be a section of a periodic function. Alright, so now I'm regarding f of x, alright, as in a full range of a periodic function with period 2L. Okay, so f of x actually is in a full range of a periodic function. It's a period 2L. And by theorem 11.1.2, this theorem is just our representation theorem of trigonometric Fourier series. Okay? Because for this function, it is piecewise continuous. Okay? And at every point, it has left-hand derivative as well as right-hand derivative. So it satisfies the requirement, the condition required in this theorem. Okay. So now, f of x, so we know that the average, okay, can be, the average is just the sum of the trigonometric Fourier series. The trigonometric Fourier series will converge at every point. Okay? This is the conclusion of the theorem. So we can have okay, so we have that. And the Fourier coefficient, of course, depends on L, depends on the length of truncation. So we have that A L0 is the average. And we have L of n. Ln. Okay, so we have that. That is what we know, right? Up to now. And the technique is that. Well, we want to, I'm sorry, forgot to put L here. Okay, so it's L. Okay, and then by this definition, this comes to okay, so you can remove L. Now, okay, so this is from the theorem, and this is from the definition. Okay. So this definition, the boundary point, we define the value at the endpoint with 0 will not affect the left-hand limit and the right-hand limit value. Okay, they are not. So they're equal. Now the problem is that when we let L goes to infinity, okay, then every point can be represented, right, for a certain series sum. Right. And we will see the changing, the evolution of the Fourier coefficients as L goes to infinity. All right, it's very important to see, we see the evolution of the L. And finally, gradually, we will turn the series sum here to be an integral. Okay, to be an integral. This is our plan, very simple plan. But we have to overcome some mathematical difficulty. Basically techniques. Okay, so now, but fortunately we know how to compute the Fourier coefficients expressed by integrals here, right? So we put the integral back. Okay, so actually I think I have to put L here. Right? Initially, I have to put the L here. But then I can remove them. Okay. So actually, we have two steps. The first of all, we have to put L and then remove them. Is that okay for you? Right? Alright? So it's correct, but actually after two steps. Okay? Okay, now so we will turn over to there. Okay? So now we turn over. So we have this is a long journey. Okay? So it's a long journey. But I will start from here. The idea is very simple, but the journey is long. All right. So let's take into it to L. plus alright, so this is basically just do the substitution here. Okay, do the substitution. And so I will erase L again, sorry. Okay. So now the inference of L here, alright, here is just the limit of the integration, okay, and the expression of the some factors in the integrand. Alright, so we turn to here. Okay, and now we decide to do one thing. Well, so we have basically we have a lot of pair, right? L pairs here. What do we have? Okay, here the I. So we decide to do one thing that well, we want to do something that this is I, L, I here, and so we have I. Maybe I write. Maybe I write here. I. Maybe it's better to write it this way. Okay, and so so we have this one. We have that one. Okay, and we let delta omega to be equal to pi divided by L. Why? Because we are going to let L go to infinity, right? So L will become bigger and bigger. So then the delta becomes smaller and smaller. This is the basic technique we use in Riemann integral, right? In calculus. So we will follow the idea. Okay? So now the expression becomes to be more clear because the L disappeared immediately. Okay, so now we will write it to pi. Oh, we still have L here, right? Lu. So we have making the effort plus here 1 over pi summation k from 1 to n. So we will let limit n goes to infinity and 1 over pi, and we turn to finite sum because this is the series sum, right? Now we turn the series sum become to the limit of the partial sum. Okay, so that's why we turn that one, and we have Fu cosine k delta omega u together dU here, and cosine k delta omega x, okay, plus Fu sine k delta omega u dU sine k delta omega x. Okay. Together. Alright, so this is a way. All right. So now we move on the name here. So we have and the integration minus L f of u. Okay. So we move the common things to the left hand side. The integration here. All right. The f of u. All right. And 1 over pi. All right. So we move everything here and keep the other thing on the right hand side, 1/2. So we have cosine k delta omega u cosine k delta omega x. Okay, here plus sine k delta omega u sine k delta omega x together and delta omega u, right? Because we have, I forgot to put something here. So I moved the delta omega here. Because we have delta omega, I forgot that. Move to here. And I forgot to put delta omega here. So this is delta omega. So I move to here. I move this one here. Okay? Don't forget them. Right, so I move them here. Alright, and basically I move to the end and the du here. Right. Okay, and we use the sum product formula in the trigonometric geometry, right? So in the trigonometry we have sum product, and so we know that. So we finally can simplify the result to be limit n goes to infinity 1 over pi L minus L f of u 1/2, okay, plus summation, okay, from 1 to n, and here is the cosine k delta of u minus x here, and delta of u. Okay, so much simplified. We have it. Okay, and we use a technique that basically we have that before. The sum here, we want to simplify the sum. We want to simplify by using the formula. Things. If I think this a practice in so this is theta, so we can regard it this as a theta. Okay, so we have cosine k theta. Okay, and we want to simplify that. So a technique used in high school is that you multiply with sine divided by 2. I hope you still remember this step, because I still remember that, okay, even though half century ago, maybe, not maybe 40 hours, yeah, about, yes, almost 50 years, almost. So, okay, so that techniques, so I just write down that, all right? I think you can check that yourself. So finally, we have sine divided by 2. Okay? And so when we divide by the sine instead of 2 again, so we finally have a formula 1/2 plus summation n minus 1n and then cosine k theta is equal to the sine. And actually, remember this formula we got that before, right? when we discussed the Fourier series, okay? But it appeared again, right? Very interesting. So the 1/2 here, we have 1/2, fortunately here, right? Very strange. Why do we have 1/2? Well, it's by the due process, right? So we have that. We are very lucky, right? And so the final result is that okay, so now, so we have the journey is going to the middle. Okay, so now we have the limit and goes to infinity, 1 over pi, L minus L. The FU, okay, here. So we have the sine n plus up. And remember, the theta is here, so it's delta u minus x, okay, and q sine 1/2 delta omega u minus x, okay, and delta du. Okay, so we have that. All right, that's good. And so we do some change of variable. So we let u minus x, this one to be equal to v. Okay, so we use the v summing variable. So we have v plus x, because u minus x is v, so here and here, and we have sine n plus 1/2 delta omega v, 2 sine 1/2 delta omega v, and delta omega v. Okay, so we have that. This is our expression. Okay, and as before, with that, we can replace the limit to be because we don't like the sine function in the denominator, right? So we replace that. Actually, when this is quite small, because you don't get omega going to 0, right? As L going to infinity. So it could be very, very small. And so, actually we can replace before we can use the Riemann effect lemma. We are going to use the Riemann effect lemma. Okay, so we can replace this denominator to this one. A very simple one. Actually, when this is very small, they are almost equal, right? We know that. So we can, and the reason is quite the same, right? I put in my lecture notes, so I don't duplicate that. Okay? Yeah. Okay. So now. Okay. Okay, so we do that before. Okay, and the good thing is that we can cancel denominator, right? And put v here. Okay, so now things becomes more and more simple. Okay, so we have that. All right, so now, the interesting thing is here. It looks very dirty, right? You have integration, the upper limit like this one and lower limit like this one, right? Very dirty. So can we fix something that extend the upper limit to infinity, and for the lower limit to the minus infinity? Can we do that? Well, a technique is by using what? Using the Lebesgue. The Lebesgue thing. Okay, so now things. So this is the trick. Okay, in this interval, right? In this interval, because from here to the past infinity, we evaluate the integral of this function. Okay, we evaluate that in degree. All right, we evaluate that, and this one is less than or equal to, because that this is a lower, and so we have upper bound is L minus x. Okay, is that okay? Because this is going bigger and bigger, and you know this one always non-negative. And actually, we can fix. So maybe I will say for x we have. So now for any, maybe I will say for any fixed x in the open interval, we have that. Okay, in open interval then, so this one will be positive, right? Always positive. Is that okay? It's always positive. And so this is the smallest. So 1 over v, right? This is the biggest one, right? This is the biggest. So I put the biggest one here, and this is v here. Okay? And also, I have to, Okay. Oh, sorry. I have to finish to stop here. So this one, this is less than 1 over. So this is the equal to. But when you change the variable again, right? So this is equal to u. So you have L. Okay. This one, and this is equal to. Okay, so we will assume that the f is absolutely integrable. Okay, so this is finite. So when this is finite, so we prove that in this range, in this interval, this function is absolutely integrable, and so by Riemann the Bake lemma. Okay, the limit n goes to infinity in this interval and the sine n plus 1/2 goes to 0. Right? So if we extend the upper limit from L minus x to infinity, we do not change anything. Okay. Similarly, from okay, so we have Alright, now we are very happy, right, to announce that we can have a very good integration range here. Okay, so I stop here. Alright, so now we are going pretty and pretty, right? So we are going pretty and pretty. And we are almost done. Okay, we are almost done to render a very good representation of integral. Okay? Alright, so I stop here and so we will have a quiz examination next Tuesday. So we will have a practice session next Monday night.